Before this story is over, you will understand why thousands of Canadian engineers still consider what happened on a single day in February 1959 to be one of the greatest acts of institutional self-destruction in the history of aviation. If that sounds like the kind of story worth following, subscribe and hit the notification bell. There is more coming. And leave a comment telling us which cancelled aircraft program you think deserved a better fate. Now, let's talk about the Avro Arrow. In the early hours of a cold morning somewhere above the Arctic Circle, radar screens would have shown the contacts moving through storm weather at high altitude, heading west. Heavy aircraft carrying weapons of a scale that made the word weapon feel insufficient. Devices capable of erasing cities, carried in the bomb bays of aircraft that had been specifically designed to fly routes over the polar ice cap that would bring them over North American targets before any ground-based defense system could respond effectively. The North American Aerospace Defense Organization would have scrambled interceptors, and the signal for those interceptors would have gone not to American bases alone, but to the northern ally whose geography placed it directly beneath the threat axis, and to the aircraft that ally had built specifically for this mission. The aircraft that would have answered that call was called the Arrow. It was Canadian. It was, by every technical assessment conducted by people who flew it, evaluated it, and studied it, including assessments made by military establishments that had no particular reason to be generous toward a foreign competitor, one of the most capable interceptor aircraft ever designed. It flew faster than almost anything else in the sky. It handled well enough that the test pilot who flew it described the experience in terms that suggested the aircraft had been designed with his specific preferences in mind. And it was cancelled, along with every drawing, every component, and every completed airframe, in a decision made over a single weekend that left over 30,000 people without employment, and left Canada's aerospace industry in a condition from which it did not fully recover for a generation. This is the story of how that happened, and why the people who made the decision were not entirely wrong, and why the people who have spent 60 years arguing that the decision was a catastrophic mistake are also not entirely wrong. Both things are true simultaneously, and understanding why requires starting not with the Arrow itself, but with the aircraft that preceded it, and the threat that both of them were designed to address. The years immediately following the Second World War produced a specific category of strategic anxiety in Western defense planning that is difficult to fully appreciate from a contemporary perspective. The Soviet Union had emerged from the war with an enormous conventional military force, a demonstrated willingness to use that force to establish a defensive perimeter of client states along its western border, and an accelerating nuclear weapons program that Western intelligence was tracking with increasing alarm. What was known, or strongly suspected, was that the Soviet military was developing long-range aircraft capable of carrying nuclear weapons on one-way missions over the polar routes that represented the shortest path between Soviet territory and the population centers of North America. The geography of this threat was Canada's particular problem. The continental United States was separated from Soviet territory by 2 oceans and by Canada itself. Any bomber flying a polar route toward American cities would cross Canadian airspace first. Canada was, in the strategic geography of the nuclear age, the approaches, the zone through which the threat would pass before it arrived at its intended destination. This created an obligation, both self-interested and alliance-driven, to develop the capacity to intercept those bombers in Canadian airspace before they could release their weapons. The Canadian Air Force already operated an interceptor aircraft that had been developed domestically, a twin-engine, all-weather platform that had entered service in the early 1950s and performed well enough that Allied air forces had shown interest in acquiring it. But the development of that aircraft had been difficult, marked by delays and technical problems that had frustrated the military establishment throughout the program. More importantly, the Soviet threat was not static. The bomber fleet that the first Canadian interceptor had been designed to counter was already being supplemented by faster, higher-flying aircraft that would eventually include jet-powered designs capable of speeds and altitudes that the existing interceptor could not match. The requirement for a successor was written before the existing aircraft had even completed its entry into service, an acknowledgement that in the technological competition of the Cold War, the relevant question was not what the threat looked like today, but what it would look like 5 to 8 years in the future, when whatever was currently being designed would actually be ready for operational deployment. The requirement document specified performance levels that no existing or planned aircraft anywhere in the world could meet. The aircraft had to reach a speed 50% higher than sound at very high altitude, achieve that performance within minutes of beginning its takeoff roll on a runway of moderate length, carry 2 crew members and a meaningful weapons load, and have enough range to operate effectively across Canada's enormous northern territories. The company that received the development contract was the Canadian subsidiary of a larger British aerospace group, an organization that had demonstrated real engineering capability with the existing interceptor, despite the program's difficulties, and that had the industrial infrastructure to undertake a program of this complexity. The engineering team that took on the requirement was led by people who understood both what the requirement demanded and what the state of aviation technology in the mid-1950s could realistically provide. The configuration they settled on was driven by the aerodynamic requirements of the mission. An aircraft that needed to fly efficiently at speeds twice the speed of sound and at altitudes approaching the operational ceiling of the aircraft of the period needed a wing geometry that was fundamentally different from the configurations that had characterized jet aircraft design in the decades since the war. The delta wing, a broad, triangular planform in which the wing's leading edge sweeps back at a sharp angle and the trailing edge runs essentially straight across the aircraft, provided several advantages simultaneously for this application. It generated lift efficiently at the high angles of attack characteristic of supersonic flight. It provided a large internal volume for fuel storage, which was critical for an aircraft whose range requirements were demanding. And it distributed the structural loads of high-speed, high-altitude flight across a large surface area, allowing a relatively light structure to handle significant aerodynamic forces. The aircraft that emerged from this analysis was large by fighter standards, not because the designers wanted a large aircraft, but because the combination of 2 crew members, 2 large engines, a substantial internal weapons bay, and enough fuel for the specified range simply required a certain minimum volume. The wingspan was approximately 15 meters. The length was nearly 24 meters. The height was over 6 meters. These were numbers more characteristic of a medium bomber than a fighter. But the performance targets required a power plant of a scale that mandated this structural envelope. The weapons were carried internally, a configuration that was not standard for aircraft of this era, but that offered significant aerodynamic advantages. External weapons stores create drag and disturb the airflow around the aircraft in ways that reduce both maximum speed and fuel efficiency. An aircraft carrying its weapons in a sealed bay inside the fuselage presents a clean aerodynamic surface throughout the cruise phase of the mission, expending its performance penalty only during the brief engagement window when the bay doors are open. For an interceptor whose primary advantage was speed and altitude, preserving that aerodynamic cleanliness was worth the additional structural complexity of an internal bay. The decision to pursue internal weapons carriage led directly to a fuselage configuration that was itself somewhat unconventional. The weapons bay occupied a substantial fraction of the fuselage's lower half, which constrained where other systems could be located and required the engines to be positioned in a way that worked around the bay geometry rather than being placed in the most aerodynamically efficient location. The wing was mounted high on the fuselage, above the weapons bay rather than below it, which facilitated access to the bay for loading and servicing, but created a center of gravity challenge that the designers had to address through careful distribution of other heavy components throughout the airframe. The production philosophy that the engineering team chose was itself unusual and controversial within the program. Standard practice for a new aircraft design at this stage of development was to build a small number of hand-assembled prototypes, fly them extensively to identify problems, incorporate the lessons learned into the design, and then transition to production line manufacturing. The Canadian team chose to bypass this sequence and design the aircraft for production line assembly from the beginning, even before the design had been validated in flight. The rationale was speed. The threat was real and urgent. The development schedule was aggressive, and avoiding the iterative prototype phase could save a year or more of development time. The vice president of engineering who made this decision acknowledged later that it created engineering problems that the prototype approach would have caught earlier and more cheaply. But he also maintained that the schedule pressure was genuine and that the approach had achieved its stated objective. The aircraft reached its first flight date on schedule. Whether the additional cost incurred by debugging a production-configured aircraft rather than a simplified prototype was worth the time saved was a calculation that different people in the program assessed differently. The aerodynamic testing program that preceded first flight was extensive and inventive. Wind tunnel testing was supplemented by a method that reflected the limitations of the computational tools available in the mid-1950s. Small-scale models of the aircraft were mounted on sounding rockets and launched to high altitude, where the aerodynamics of the full-scale aircraft at the target flight regime could be simulated and measured by instrumentation in the model before it returned to Earth. The data from these tests identified several areas where the initial design needed refinement, including modifications to the wing's leading-edge geometry and the addition of a specific aerodynamic feature at the wing's midpoint that improved airflow control at high speeds. The construction used aluminum alloys as the primary structural material, supplemented by magnesium alloys where weight reduction was critical, and by titanium in the areas around the engines where temperatures were highest. The titanium component was limited not primarily by cost considerations, but by availability. The material was already committed in large quantities to an American high-altitude reconnaissance aircraft program that had priority claim on the global supply. An engineering problem that emerged during the testing phase illustrated both the technical sophistication of the design and the difficulty of developing genuinely new technology on an aggressive schedule. The aircraft used a fly-by-wire control system in which the pilot's inputs were translated into electrical signals that commanded hydraulic actuators rather than being directly connected to the control surfaces through mechanical linkages. This approach was necessary because the aerodynamic forces acting on the control surfaces at the aircraft's intended operating speeds were too large to be overcome by a human pilot working through mechanical connections alone. The forces required to move the control surfaces would have been physically beyond the pilot's capacity. But a fly-by-wire system without artificial feedback provides the pilot with no tactile sense of how hard the aircraft is working or how close it is to the limits of its flight envelope. Test pilots complained that the control inputs felt disconnected from the aircraft's actual behavior in a way that made precise handling difficult. The engineering response
was to develop a system that artificially recreated the feel of mechanical control, a hydraulically generated resistance in the control column that varied with the aerodynamic forces on the surfaces, giving the pilot the tactile feedback that the direct mechanical connection would have provided.
This was, by the accounts of those who developed it, one of the first implementations of artificial force feedback in a production aircraft control system. The program's first serious setback arrived from an external direction that the Canadian engineering team could not have anticipated or controlled. The specific engines that had been selected for the production aircraft, a domestic development and a foreign alternative, both chosen for their compatibility with the aircraft's performance requirements, were cancelled by the companies developing them for reasons related to other programs and priorities. The aircraft was left without its intended power plant at a critical point in development, requiring the substitution of an alternative engine that was available but was not optimally matched to the airframe's requirements. The substitute engine was heavier than the intended power plant, which shifted the aircraft's center of gravity in a direction that required adding ballast weight to the nose to restore the proper balance. Ballast weight is dead weight. It contributes nothing to the aircraft's capability and reduces performance across all parameters. The engineering team managed the problem, but the aircraft that entered flight testing was measurably heavier and correspondingly less capable than the design that the original power plant would have produced. A second disruption arrived from the military customer. An evaluation of a full-size mock-up of the aircraft revealed that the Canadian Air Force wanted to change the weapons and sensor systems specified for production, replacing the existing fire control and weapons package with a newer American system that was at that point still being developed and did not yet exist in hardware form. The manufacturers warned that incorporating an unproven system would require extensive redesign and would cause significant delays. The warning proved accurate when, less than a year later, the American system was cancelled before it ever reached completion, leaving the Canadian program having undertaken costly redesign work for a component that would never exist. These accumulating difficulties were taking place against a background of political and strategic change that was independently undermining the program's rationale. The formal public unveiling of the completed aircraft on a day in October 1957 was intended to be a moment of national celebration. Thousands of people assembled to see the most advanced aircraft Canada had ever built. Instead, the event was overshadowed to the point of near invisibility by news from the other side of the planet. The Soviet Union had launched the first artificial satellite into Earth orbit on the same day. The psychological impact of that announcement on Western defense thinking was profound and immediate, and it was directly relevant to the Arrow's future. The satellite demonstrated that Soviet technology had achieved the capability to place objects into orbit, which implied the ability to follow a ballistic trajectory from Soviet territory to targets anywhere on Earth. The implications for air defense were immediate and stark. An intercontinental ballistic missile does not fly through the Arctic on a path that interceptors can reach. It ascends into space, follows a ballistic arc at altitudes and speeds that no aircraft can approach, and descends onto its target in minutes rather than hours. All of the elaborate infrastructure of radar networks, interceptor aircraft, and air defense doctrines that had been built to defend against the manned bomber threat was irrelevant against a threat that arrived from space rather than through the airspace that aircraft occupied. The strategic reassessment that followed this demonstration was neither uniform nor immediate. The manned bomber threat did not disappear, and military planners were appropriately cautious about abandoning existing capabilities before replacements were proven. But the direction of the reassessment was clear to anyone paying attention, and the Arrow's program office was paying attention. The aircraft had been designed to solve a specific problem.
The extent to which that problem was about to become less urgent, or to be supplemented by a different kind of problem that the Arrow could not address, was a question that now hung over every budget discussion and every program review. The political context within which these technical and strategic questions were being evaluated was itself complicated. The Canadian government had recently signed a formal agreement creating a joint air defense organization with the United States, integrating the two countries' air defense systems under a unified command structure. The logic of this integration was sound. The geography of the threat made the defense of Canadian and American airspace a single operational problem, rather than two separate national problems. But the integration also created channels through which American industrial and political interests could be brought to bear on Canadian procurement decisions, and those interests were not neutral on the question of whether Canada should continue developing its own interceptor. The American defense industry had its own interceptor programs, its own investments, and its own interest in having Canada be a customer rather than a competitor. The political instrument through which this interest was expressed was the offer of an alternative to the Arrow, an American-developed surface-to-air missile system with a nuclear warhead that could be stationed across the Canadian North and would, in theory, destroy incoming Soviet bombers before they reached their targets without requiring the expensive fleet of interceptor aircraft that the Arrow program would have demanded. The economics of this alternative were presented to Canadian decision-makers in terms that were difficult to argue with on the numbers alone. The missile system would cost less than the Arrow program and would handle the same threat. What the economics did not capture was what Canada would lose by accepting the missile system and abandoning the aircraft. The engineering talent that had been assembled to develop the Arrow, the industrial infrastructure that had been built to produce it, the institutional knowledge and technical capability that the program represented, none of these could be preserved without something meaningful to work on. Accepting the missiles meant dismantling the program and dispersing its people. It meant that the investment in capability that the Arrow represented would produce nothing lasting, because the capability itself would be destroyed along with the hardware. The first flight came in late March 1958, delayed from the originally planned date, but still within the range that the aggressive production line development approach had targeted. The aircraft performed well. The test pilot who flew it reported that the handling at supersonic speeds was better than he had expected, that the approach and landing characteristics were satisfactory, and that the aircraft appeared to meet its design specifications across the parameters he had been able to evaluate in the early flights. By the third flight, the aircraft had exceeded the speed of sound, and not by a marginal amount.
The speed achieved during a climbing profile exceeded 1,600 kilometers per hour, and on subsequent flights, the aircraft approached twice the speed of sound without appearing to have reached the limit of its capability. The test pilot's assessment was unambiguous. The aircraft did what it was designed to do. The engineering team's design had worked. The years of difficulty with cancelled engines, redesigned weapon systems, and accumulated delays had produced, in the end, an aircraft that performed as promised. None of this was enough. The political and strategic forces arrayed against the program had been building momentum for 2 years, and the first flight success, while genuine, came too late to reverse the trajectory that events had taken. The government had been signaling its intention to cancel the program for months before the first flight. Internal government documents showed a clear preference for the missile alternative and a growing conviction that the cost of the Arrow, which by this point represented somewhere between a fifth and a third of the total Canadian defence budget, was not sustainable, regardless of how well the aircraft performed technically. The Army and Navy,
whose budget allocations were being squeezed by the disproportionate share of defense spending consumed by the Air Force program, had their own institutional interests in seeing the program ended. The final decision came in February 1959. The program was terminated immediately and completely. Not suspended, not reduced, terminated. Every employee received notice on the same day. The company's leadership learned about the decision from newspaper reports rather than from the government officials who had made it, which said something significant about the quality of the relationship between the program and its political overseers at the end.
The most consequential and most debated aspect of what followed was the order to destroy the completed aircraft, all production tooling, and all technical documentation. The rationale offered publicly was that the aircraft's design incorporated sensitive technology that could not be allowed to fall into the hands of adversaries. This was not entirely implausible. The aircraft did incorporate advanced technology, and Soviet intelligence collection efforts against Western defense programs were real and active. But the same argument could have justified securing the technology rather than destroying it, and the completeness of the destruction went well beyond what security concerns alone could explain. 6 completed aircraft were cut apart and melted down. Engines were destroyed. Production jigs and tooling were demolished. Technical drawings and specifications, the accumulated product of years of engineering work, were disposed of. The physical record of what Canadian engineers had accomplished was made to essentially disappear, save for a few surviving models and mock-ups in museums and the drawings that individual engineers had preserved privately in defiance of the destruction order. The people who had built the aircraft dispersed within months. A significant number went south to American aerospace companies and government agencies. Some of the most capable engineers from the program contributed to the American space effort in the years that followed, working on projects that benefited from the skills they had developed on the Canadian Interceptor program. Others went to Britain, where at least one member of the Arrow's leadership team contributed to the development of the supersonic passenger aircraft that eventually entered service in the 1970s. Canada, having cancelled its own Interceptor, needed to replace it with something. The something it eventually chose was an American aircraft. An older design, less capable than the Arrow in every performance parameter, purchased in numbers that represented a significant ongoing cost. The political fallout from this decision contributed to the collapse of the government that had made it within a few years, though correlation and causation are difficult to separate cleanly in the turbulent Canadian politics of that period. The Arrow's legacy has been contested ever since. The case for the cancellation, made by its defenders over 60 years, rests on several arguments that are individually reasonable and collectively difficult to dismiss entirely. The cost of the program was genuinely extraordinary for a country of Canada's size and economic weight. The strategic environment was genuinely changing in ways that reduced the importance of the manned bomber threat relative to the ballistic missile threat that no aircraft could address. The requirement for enough aircraft to adequately defend Canada's territory would have required procurement numbers that made the program's economics even more challenging. And the alternative systems that were available provided meaningful capability against the actual threat at lower cost, even if they represented a less technologically ambitious solution. The case against the cancellation rests on arguments that are equally difficult to dismiss. The aircraft was technically successful. It flew. It performed as designed, and by the assessment of every qualified pilot and evaluator who had contact with it, it was a genuinely exceptional machine. The destruction of the hardware and documentation was not a necessary consequence of cancellation, but a separate decision that compounded the program's loss. The technology and the institutional knowledge it represented
could have been preserved.
And the dispersal of the engineering talent that followed the cancellation represented a human capital loss, whose consequences were felt in Canadian aerospace for decades, as the country found itself importing capabilities it might otherwise have developed domestically. The claim, made occasionally in the years since, that an evolved version of the Arrow might have remained competitive with aircraft designed and built decades later reflects a certain kind of sentimental reasoning that the technical facts do not fully support. Aircraft technology advanced dramatically in the 20 years after the Arrow's cancellation in ways that could not have been anticipated from the 1950s design baseline. The Arrow was exceptional for its time, and might have been exceptional for somewhat longer than its time, but engineering trajectories do not extend indefinitely. What was lost with certainty was not a specific aircraft that would have remained relevant indefinitely, but a generation of engineering momentum, the accumulated capability, confidence, and institutional knowledge that comes from completing a difficult program successfully and then building on that success. Canada had, in the Arrow program, demonstrated the ability to design and build a world-class military aircraft entirely with domestic talent and resources. That demonstration, if it had been followed by continued investment and continued programs, would have created a foundation for capabilities that the country has since had to acquire from foreign sources. The drawings that a senior draftsman kept in a personal safe for decades, against orders and against the explicit intent of the destruction program, are a small physical embodiment of a large historical argument that what was built deserved to be remembered, that the achievement was real even if the program did not survive, and that the decision to destroy the record rather than preserve it reflected something about the decision-makers' attitude toward what they were eliminating that went beyond the stated security justification. For Canadians, the Arrow occupies a place in national memory that is disproportionate to its operational history, which amounts to a few dozen test flights before the program ended. It is remembered not for what it did, but for what it represented and what it might have been. The engineers who built it were good enough to build it. The country that commissioned it was capable of producing it. The decision to end it was made for reasons that were understandable in the context of their time and catastrophic in their consequences. And both of those things are true simultaneously. That combination, genuine achievement, genuine loss, and a decision that was neither entirely wrong nor entirely right, is why the story has not faded in 60 years, and why it continues to be argued over by people who were not yet born when the aircraft flew its last flight and the cutting torches went to work on what remained. The Arrow never defended a single kilometer of Canadian airspace. It never intercepted a single Soviet bomber. It exists now only in fragments in museums and in the memories of the people who built it. But it was real, and it worked, and it was destroyed before it had the chance to do the job it was designed for. Whatever else might be said about that outcome, it is a fact that the people who were there never stopped finding difficult to accept.